First of all, I'd like to thank the organizer, Professor Bae, for his invitation and for making this great conference. And also thank you all for your coming in this very early morning. So this is a joint work with Professor Emin Chen at the Simon Fraser University. Simon Fraser University is at Vancouver, Canada. So I used to work there as a faculty member. Okay, so let me begin with the goal and some preliminaries for some terminologies. And then I want to tell you about the explicit isogeny theorem for the general rank case. And for the basic method for this general rank case, so we use these two important methods. So effective Chebotarev density theorem, and we have to also deal with a different divisor of the upper bounds. But somehow our explicit, I mean, even though I'm saying the explicit isogeny theorem, there is one term I couldn't make it really explicit. So but for that part, but the rank 2 case we got a better result. So the rank 2 case, it was possible to make that part is also even more explicit by using Newton polygon idea of the exponential function associated to the rank 2 Drinfeld module. Okay, and then I want to also discuss the surjectivity. Well, I mean, if we get this explicit isogeny theorem for the rank 2 case, it can be applied to discuss the surjectivity of the Galois representation associated to the torsion parts of the rank 2 Drinfeld module. So that part I'll just mention it very briefly. And also Gardeyn also worked on the explicit isogeny theorem, well, effective, I should say, effective isogeny theorem version. But there is I want to tell you what's the then difference between his work and our work. And the last part, I think by this time I'll run out of the time. So if time permits, maybe I should be able to sketch the main result. Okay, so as I mentioned before, our goal is basically we want to discuss isogeny theorem for rank R case, and more explicit version for the rank 2 case, and then surjectivity result. I mean, I already mentioned it in the previous slide. Okay, here is the basic notation. So we're going to use it for this talk, but still, I mean, standard notation. Fq is a finite field about Q. Q is a prime power. F for this talk, I mean, we will use this capital F denote the rational function field, and A is a polynomial ring. F bar is algebraic closure. And K is a finite extension of F. So K, of course, could be the same as the rational function field, but K doesn't have to be exactly the rational function field. This is a sort of general case. And so in this talk, what we mean, I mean, this is generally what we mean by the prime P or place P. So we mean the discrete valuation ring with the fraction, field of fractions K, and maximal ideal P. And also infinity, this notation is for the infinite place or infinite prime determined by the degree of valuation. And as K, sometimes I may use this notation that's collection of all the places at infinity lying above prime at infinity. Okay, capital L is a finite extension of K, and constant field of L means we will use this notation. So later, if you see this notation, oh, what is this? What is F sub L? It's actually F sub L. What I mean by that is constant field, which is really algebraic closure of the finite field in L. So maximum possible constant extension part. Okay, geometry extension degree is when you have the extension of L and K, there is an intermediate field, let me say K prime. So L, K prime, and K, so top to middle L over K prime is called the geometry extension degree. What is K prime? K prime is the maximum possible constant field extension of K from the bottom. And degree of prime P, I mean, that's the typical standard notation for the residue class field degree. So this one this is a standard one, just in case I wrote it down. Okay, tau is the map raising an element to its q's power. It's x to the tau, x will be x to the q. And Drinfeld module is given by two, one is homomorphism I. I mean, this could be, this can be taken as inclusion, or I mean, just general homomorphism. FQ algebra homomorphism from A to K tau. So what I mean by K tau is the ring of formal polynomials with twisted multiplications with the tau. And phi sub A has constant term, this iota A, and the image of phi is not contained in K. This is called the Drinfeld module. And rank R Drinfeld module is completely determined by the image of T. So you can actually get the general, I mean, you can determine general polynomial for any A. If you know T, then you can determine the image of the Drinfeld module. And this, the highest coefficient part, I mean, this part is called the discriminant of phi. The reason why I call it discriminant of phi, I guess that is involved with the reduction, good reduction or bad reduction of the Drinfeld module. Okay. And as you see, okay, let me go back. So this is if you apply lambda, then you're gonna get the polynomial in lambda. So that's definitely polynomial. And if you take all the roots of the polynomial, that is the torsion. That is called the A torsion point. And also you can talk about that for the ideal also. Then this torsion point has a structure of A quotient A, so A to the R, depending on your rank. If rank is 2, then that's you have a 2. R will be 2, so you have 2 copies of it. And this is the important notation through this talk. We're going to use it. This is the field obtained by a joint A torsion point. So which means phi is involved with Drinfeld module phi and also A. So it's depending on phi and A. And 4 is ideal, but okay. A good reduction, P is a prime of K and OP is the valuation ring of P. Then when you say the Drinfeld module has integral coefficients at P, that means phi sub A has coefficients in this integral valuation ring. And the reduction mod P, the reduced Drinfeld module is denoted by this. And when you say the good reduction, first of all, I mean, it should have, I mean, if a phi has a good reduction, that means, what does that mean? That means phi is isomorphic to phi itself. Maybe can be definitely can satisfy these conditions. But if not the case, phi has to have some isomorphic Drinfeld module psi has integral coefficients, and also it's a reduced module preserves the same rank R. Then we say it's a good reduction. But the rank decrease, then we say it's a bad reduction. And there is a result that if I has a good reduction at P, if and only if this is the collection of all the torsion, L torsion, GK module is unramified at P. And what we mean in general, unramified at P, what does that mean? Then that means inertial group acts trivially there. Okay, this result is analog version for the Drinfeld module of Ognaran-Shafarevich in the theory of abelian varieties. Then, if a phi is a Drinfeld module which has integral coefficients at every finite prime P, then phi has a good reduction outside of the set of primes S. But S, I mean, what we want to exclude is S actually includes the prime at infinity and the primes dividing the discriminant. That is the trouble, guys. And in particular, these modules are unramified outside of this S collection in union with prime L. Okay. Then the P torsion points brings us Galois representation to this torsion, the automorphism of the torsion module, and GK is absolute Galois group. And we use this Artin symbol. Okay, if a phi has a good reduction at P, Then elliptic Tate module, this is a standard terminology. Elliptic Tate module defined by this is unramified at P as long as this prime P and this prime L is a prime. If they are distinct, then this elliptic Tate module is unramified. Okay, then what is the Tate conjecture for rank R Drinfeld module? Tate conjecture is this. Okay, so this is Artin symbol I mentioned just before, and then you take the characteristic polynomial. This is a characteristic polynomial of this Artin symbol on Tate module. Then this characteristic polynomial is independent of this L prime L. That is a known result. Then when you have the two Drinfeld module of rank R, and A sub L denotes the elliptic completion of A, then we can collect all the homomorphisms between two Drinfeld modules, and you can consider all the homomorphisms between two Tate modules, elliptic Tate modules. Then between them, there is an isomorphism. This is called the Tate conjecture. Okay. Then the consequence of Tate conjecture is the isogeny theorem. Then what's the isogeny theorem? Two Drinfeld modules are k-isogenous if and only if their corresponding characteristic polynomials are the same for all but finitely many primes. So for most of the primes, they are the same. Then our goal is we want to find an explicit and effective version of the isogeny theorem. So what do you mean by explicit and effective version? So we are interested in this. Okay, so let's take the phi and phi prime. They are non-isogenous. Okay, they are non-isogenous. Then corresponding characteristic polynomials may be different. Then we want to find what is the smallest, what is the, I should say this, okay, not smallest. So what is the, then we can compute the degree of the primes P. Then what is the really explicit upper bound? Okay, so that will depend only on phi and phi prime. It's not depending on other guys. That's the basically goal for this work. Okay, so as I mentioned before, I'll show you the result. So this is a little bit partially. I'll tell you why that is a little bit partially. So this is a notation we're going to use. So here tau kp is the minimum value of valuation P. AI phi is the coefficient of the Drinfeld modules. So when you have the Drinfeld module, this value is completely determined. That's explicit value. And through this talk, this is the important value, gamma L. Gamma L, what is that? That's constant field extension degree. You remember this notation was the constant field of L. So you take the constant field extension degree, that's gamma L. Then this torsion field, the K is joined by this torsion of the Drinfeld modules. This is finite over FQ. That part is known already. So then we can measure the constant field extension degree from the bottom FQ. We're going to use the notation gamma phi, because if phi is given, then we can determine this, because A is taken for everybody. Okay, of course, in general, we realize, okay, A is pretty general. Well, this is explicit, but this is not explicit. That part is the trouble part. Okay, this is the result. So K is a finite extension of LF with the constant field of Q and genus G. And phi and phi 2 are non-isogenous. Before I use phi and phi prime, but I changed the notation phi 1 and phi 2. And S is a set of the primes lying over infinite place, and the trouble guys, the primes dividing this discriminant values. And if P is the prime of K, satisfying, okay, the two corresponding characteristic polynomials are distinct. They are different, but among those guys, we take the minimum guy, the smallest degree guy. Okay, we take that one. So we assume, okay, there exists such a P. Then what will be the upper bound for this degree? That was the effective version. We got this bound, this explicit bound. Then you may wonder what's M naught, C, Q, R, W. But these values, I'm going to explain in the next slide. This is a notation. But this red one, WY, I put this red color because this is the part which is not completely explicit. So if Drinfeld module is given and K is given, then all the other parts are completely determined. So let me show you here. So see, S is the geometry extension degree. Well, that's explicit. L is the rank of the Drinfeld module. Of course, CL, DL, that's completely, fixed value. So we can compute it very easily. So all these values are very explicit. Everybody looks complicated, but it's very simple. It's a fixed value. So it's constant. But W is the part, okay, it's defined like this. But here you can see this lambda, but lambda is involved with tau. Okay, tau doesn't matter. Tau is easy to compute. But this is the part we have a little bit trouble. So G phi 1 and G phi 2. So let me explain G phi 1 and G phi 2. G phi 1 and G phi 2, this is the part which is related to the gamma guy. Gamma sub phi 1, gamma sub phi 2. Okay. So I'll give you the gamma sub 1. Yeah. That one I'll give you more detail about the gamma. Yeah.
What is log star?
Oh, log star. See, yeah, this is a notation we use. We take it for the simpler notation. So log star x is the, if x is bigger, then you take x. But if x is smaller than 1, you go with it as 1. That's for the consistency of the notation for the technical part of the proof. Okay, in the rank 2 case, as I said before, it's possible to make all the terms explicit. The way, I'll give you the detail, but this is an overview first. The way we were able to do it is we use that value is involved with the successive minima of the lattices. That part can be determined by the Newton polygon idea. So we have to deal with this prime at infinity, the infinity valuation of the different divisor, and also prime at the finite prime case. Infinite prime case, we use the Newton polygon idea, but the prime case, we use the Gauss's work. So I'll give you a little bit more detail about what I mean by Newton polygon idea of the exponential map. Okay, so for that, so rank 2 case, so I said, okay, we have exponential map. So what I mean by exponential map is by uniformization theorem, there exists a lattice. This is C infinity. Oh, maybe I didn't explain C infinity. So what I mean by C infinity, this is the completion of the algebraic closure. Okay, completion at infinite place. So you can find the lattice of rank 2 and surjective analytic function that which is exponential map. Satisfying this diagram commute. So this diagram commute is, this is a multiplication by A map, this is a Drinfeld module map. So between these guys, we have this commutative relation. And you can also, if you want, you can normalize it. Then this function is called exponential function associated to the phi. So when you have the Drinfeld module, you can get this exponential function that is uniquely determined by the previous properties in this form. So you can write it down clearly. So Newton polygon is involved with these coefficients. Okay, so and here, okay, this is a notation. I wrote it. I actually made a switch the order. So sorry about that. The rank R case, I gave the result, and the inexplicit part was involved with G. Right? You guys remember G phi? So if we go back. So let me go back a little bit. Well, I think, so let me go this way. I think this is quicker. Okay, so if we go back, so please forgive me. Yeah. Yeah, W. Okay, so this is the part. Okay, this is W part. This is the result, main result. And W part was involved with G phi. So G phi, I didn't put the definition there, but G phi, what I mean by that is exactly this extension degree involved with the lattice, because I had to explain the lattice first. So this guy, but in the proof, actual value we had to deal with is gamma phi. But gamma phi is bounded by, it's not possible to make this part explicit because it's involved with all the torsion points. But it's known that this gamma phi is bounded by G phi, this value. This is bounded by this extension degree involved with the lattices. Then G phi is, because infinite bar, what I mean by infinite bar is you possibly have more primes lying above infinite place. So you take all these values, you take the minimum value is defined to be G phi. Then you can bound this value by using the successive minima of the lattices. That's the place we had to deal with that. This part is actually G phi value. This one, Gardeyn worked on it. Okay, he got the result. So we looked at their result, his result, and we wanted to make it explicit. Okay, so this is a general definition for the lattice. And what I mean by successive minima, I already mentioned it. So what I mean by that is when you take the elements from the lattice, whose absolute value, this absolute value is from the infinite place, q to the minus degree lambda. Okay, so this absolute value from the infinite place. Then you take the value, absolute value is bounded by kappa. And then ith successive minima, for example, let's say first successive minima means, okay, bk contains just one number, which is k linearly independent. You take all such kappa, and then you take the minimum value for kappa. Then that is your new one. And then you deal with two linearly independent guys, that's your new two. So you find the new one, new two, new out, which is called the successive minima of lambda. Of course, that's a definition, we can understand it, but in general, how are you going to determine it? That's the hard part. Okay, so what I mean, so I want to explain the result for the Newton polygon from this exponential function. So if you, this is a rank 2 case, so we have degree 2, and J phi denotes the J invariant of the Drinfeld module, which is defined by this. And m is the least positive integer such that this v is degree v infinity, the valuation at the infinite place. So minus the valuation of J invariant is bounded by q to the m plus 1. You take the smallest positive integer m. This is plays the important role, we realized. And then depending on case, you have the explicit value involved with your coefficient of the Drinfeld module. And the Newton polygon of the exponential function is determined exactly depending on your J invariant. The first case, J invariant, okay, this negative valuation of J invariant is bounded by Q, or it's bigger than Q, but it's different from Q to the m plus 1, but it's bigger than Q, but it's exactly equal to Q to the m plus 1. Depending on these three cases, it was possible to determine the Newton polygon shape exactly. So you don't want to know the details. The important thing is depending on the condition, you know how it looks like. Then by using that information, it's possible to make this bound for the at infinite place for the different divisor. Its bound is given by these values depending on your J invariant. Because if phi is given, your J invariant value is determined. So you know where you have to go. And kappa is also determined by your Drinfeld module. And if the prime, the valuation of P, this one we didn't use a Newton polygon. This is the idea from the Gauss. So I don't have much detail for that. Okay, combining these two results for the rank 2 case, it's in general we can get the degree of the different divisor. This is the value we wanted to get. We need it actually for the explicit isogeny theorem. So So the bound, if you see, okay, A is given, okay, this is explicit, this is explicit. You may wonder what is eta, what is delta. So the definition is in the back, sorry. So delta is this. J invariance denominator part. That's easy. So delta is completely explicit. And eta is all the product of finite primes such that phi has Bade reduction. So that means the bound is sensitive to the Bade reduction, the primes, which gives you the Bade reduction. Sorry. So I think. Okay, here is the place. Okay, so this is eta and delta phi. So this is the part, Bade reduction part. Okay, so and another thing. So two ingredient. One is we have to deal with the bound of the different divisor, and the other part we have to make it explicit that G phi part. So upper bound of the extension degree of the constant for this gamma G phi is actually we have to deal with gamma phi, but gamma phi is bounded by G phi. That's why we put it as an upper bound for G phi there. But if we can, basically we want to make this value, we need the information about this extension degree of constant field part. But we got this explicit, okay, this is the result. It was possible to get this explicit bound. So this is a explicit, kappa phi is also explicit value. I showed it before. And S1 is given by the valuation at the coefficient. So how do we get this result? The reason for the previous inequality is gamma phi is bounded by G phi. This is proved. And concerning this term, we have a good result from the Gardeyn. So Gardeyn got this bound, okay, that is bounded by this successive minima value. And this successive minima value, okay, he got the general, he deal with, this is a rank 2 case, but his result is for the rank in general. You can guess it. The question is, the motivation for the Newton polygon, we wanted to make this part explicit, and how are we going to make it explicit? But from the Newton polygon's idea, it was possible to make this successive minimum value clearly, depending on your J invariance bound, where you are, depending on where you are, it's possible to make this value very explicit. Okay, that's the whole point. Okay, so this is the notation. So all the notation is given already before. So kappa phi is also very explicit depending on your J invariant value. This is also given before. Okay, so this is a result for the rank 2 case, explicit version for the isogeny theorem. And phi 1 and phi 2 are rank 2 Drinfeld A-module which are integral, but they are not K-isogenous. And we put we had M, but for each Drinfeld module, we have M1 or M2 satisfying the inequality. And we have different divisor. And S is the union of all the primes of Bade reduction. Then assume that P is a prime of least degree such that the corresponding characteristic polynomial are distinct. Then the degree is bounded by this guy. So this is explicit value, This red part is the part we have to deal with. This W is given by this. So this is explicit. These guys, everybody can be computed, but this is a, let me go back. So delta, you remember eta is the part involved with the Bade primes. And delta is explicit when you have the Drinfeld module. Your J invariant is given by this coefficient. So it's easy to determine right away. So this is a result. So the rank 2 case, we got the satisfactory result. But as I mentioned before, in general, it's not completely explicit because of that. G phi, we couldn't make it explicit. That's the still open question. And when you try to use, okay, then you may wonder, okay, for the higher rank case, why don't you use Newton polygon then? But we thought about it, but its complexity goes very rapidly high, so we didn't even, try yet. So, that part is still open. Okay, so maybe we think that maybe the new techniques using weaker information maybe will help for the explicit boundary, so we don't have the idea yet. So I do welcome to get any suggestion. Okay, so for the general rank case, I want to tell you some sort of strategy. General strategy follows from the Sayre 1981 work, adapted to the Drinfeld module situation. Then what's the difference between Sayre's work, number field? Of course, the biggest difference is Sayre's work is a number field case, and our work is a Drinfeld module situation. And as a tool, the result, the biggest difference is he used also effective Chebotarev density theorem for his tool, but his tool, Chebotarev density theorem, is under the GLH, generalized Riemann hypothesis. So his work is more like it's conditional work. But our case is better because GLH holds for the function fields case. That's the better part. But the harder part is, life is, I think, somehow fair. So one is better, but the other one is get worse. The worst part is we had to deal with wild ramification when bounding the different divisor. This kind of behavior, it didn't happen for the number field case. That was the part. So I think it's fair. Okay, and also, so Gardeyn's, I'll tell you about the comparison between Gardeyn's work and our work. And I think what we try to do is by using the defining coefficients, we are trying to make all the terms very explicit for the bound of the different divisor. That was our attempt. Okay, so these let me explain these methods. What was the result for this? Okay, so this is a sort of prime number theorem for the function field case. So number of primes with a certain degree, how can you determine this guy? And this is approximately this with this error. Then the effective Chebotarev density theorem, under this lemma, it's possible to get this Chebotarev density theorem. So we use the Murty-Shirks. We followed his line, and we using this lemma, we got the bound for the Chebotarev density theorem. So K is a finite extension of F. It's the same as the previous way, but the Q naught is we made a little bit more general. And E is a finite Galois extension of K with the Galois group G. And C is a conjugate class C with a certain condition. So don't pay attention to this condition too much. So this is a different divisor. Then Chebotarev density theorem. Okay, more tau prime. This sigma prime is also a bit technical, but you can also consider sigma and sigma prime can be taken as the same guy. But we wanted to make it general. So sigma is the divisor, which is a summation of all the primes, which is ramified in E in the extension. Then the B value can be determined explicitly. So when you have this function field extension degree, then you can determine this ramified primes, and you know the different divisors. So these are the explicit value. Then if n is bigger than or equal to this bound, this is explicit bound, n is congruent to k mod m. So this k is a previous k actually. This is the k is tau k. This this k part. Then there exists a prime p outside of this ramified. So that means it's unramified primes, such that the degree of prime is exactly guarantees the n. And the Frobenius map is a given conjugate class. That's the Chebotarev density theorem we used. So this bound is heavily involved in our isogeny theorem bound. That contributes a lot. And okay, for the upper bound of the different divisor, rank all case, so we got the result this. We got this degree of this bound is given. This is a general case, rank all case. we got this L is given. L is just the degree, Q to the degree of this prime L. So everything is explicit. S is a geometric extension degree. And lambda phi is this value. This is explicit. But this is the part we have to, this degree, you may wonder what is the degree of this part. The degree of radical kx, what we mean by that, you take all the non-zero valuation, you take the summation of the degree. That's the definition for the radical part. Okay, then we use, for this one, we use the mounting information from the Newton Polygon. As its corollary, you can also get the result for the two Drinfeld modules, and k tilde for two torsion points, you take the composite term. So I wrote it as a k tilde. You can also get the degree of this different divisor for k tilde, sort of similar degree. But so we had to use this for the final version. Okay, then application, I mentioned that we have an application to the surjectivity result for certain cases, not for all the cases. So certain case, which is a Gardeyn case, we call it. What is that? Is phi is a rank 2 Drinfeld module without the CM, complex multiplication. Then the image of this Galois representation lies in the normalizer of the Gardeyn subgroup, but not in the Gardeyn subgroup. In that case, by using the explicit isogeny theorem for the rank 2 version, we are able to get the bound for the degree p. So degree p is bounded by this value. This is, you remember this looks very, very similar to the bound involved with explicit isogeny theorem. So we can actually determine this bound for the degree p. So let me go back. To talk about this surjectivity, there is of course there is other possibility like a Borel case, Gardeyn case, a few cases. So Gardeyn is one of the case. So for Gardeyn case, we are able to use the isogeny theorem. So that's the sort of merit for using explicit isogeny theorem. Okay, so then Gardeyn also proves an explicit effect. Well, not exactly explicit. I want to say effective isogeny theorem. Then, as I mentioned before, then what's the difference between his work and our work? Then, for explicit isogeny theorem, the major ingredient is how can you bound the different divisor. That's the hard part. So our case, we got the bound like this, and the Gardeyn's result is this. Then you may wonder, oh, whatever the delta phi, well, this is a different guy, okay? This is just discriminant. That's explicit value. But this delta phi looks similar, right? But it's different guy. So then you may wonder, oh, this looks much more complicated than this. But actually, it's not the case. This is a trouble guy. Delta phi is hard to determine. So actually, I loved his bound, but I couldn't. It was not quite possible to make it explicit. So that was the beginning part of our work. So in Gardeyn's result, delta phi is. I didn't put down the definition because definition is very complicated, depending on the places. So he defined this delta phi as a sort of divisor, satisfying degree valuation. So if P is an infinite place or finite place, I mean, depending on that, he defined it. And this delta phi is a divisor heavily involved with the lattices. But it's hard to compute it, but still it can be determined from the Newton polygons of exponential functions. So Newton polygons of the exponential function associated to this Drinfeld module phi. So for the rank 2 case, his delta phi was able to be determined. But we claim that we got a sort of different bound, which is explicit. And Chen Lee, so Chen is my coworker and L is my initial. So our method is the entire Newton polygon. And also we used, for this work in another paper, so we used, Galois, Galois here. So Galois is a theory of Drinfeld modular forms. Nice result. And also we used Mike-Rosen's theory for the formal Drinfeld modules, my formal divisor. And also two other places of difference. So if I compare the both work. So for our Chebotarev density theorem, we use a multi-choice version. And there is another version, which is Gardeyn and Gardeyn version. I mean, for the Chebotarev density theorem. So Sayre and Gardeyn basically use that line. Okay, so Sayre's version is the number field version. Gardeyn is sort of used this function field version. But we used the multi-choice version because we thought that their bound, I mean their version and their bound for n is sort of easier to the effort to reduce the size of the constants in the different divisor bound. So especially, the dominating terms. Okay, the constant in front of the dominating terms. We wanted to make the reduction of the size. For that, we thought that multi-choice bound was sort of more useful. So that was also a difference. And also, second part, I put down this comment. If we look at our bound, if I go back, our bound is very heavily, it looks like heavily involved with L. Okay, this looks pretty dominant term, but actually, in his bound when he tried to use this bound for the application, in a sense, the Galois surjectivity, we realized that we have to deal with the degree of this torsion field. And in that case, we realized that we had to multiply by n prime. N prime is a geometry extension degree. And this guy is also, anyway, cannot be much explicit. So that's, anyway, it's bounded by L to the some power. So we realize it's end up with, anyway, depending on L value. Okay, this is the sum of the selected references. We used Galois, Gauss, Multi-Shirk, and Sears, and Taguchi is over here. So, yeah. So we have Taguchi. Yeah, we have so many good people here. I feel very honored. And this is the result, Sayre's result. Sayre got the isogeny theorem version, and this is the Gardeyn's result, explicit isogeny theorem. And these are the recent work with my coworker. So in this paper, we discussed the Newton polygon idea. And this paper, we were trying to make it explicit for this delta sub phi value. And this is mainly the paper, for this talk. And thank you. But we have 5 minutes to you. So we have an option though. I can stop here, or I can talk about 3 more minutes to give you a little bit more sketchy. But or we can I can answer your questions. Yeah, maybe I'll just finish here.